All right, let's start over. So you flipped your coin 100 times. How many times do you expect that that coin landed on heads? 50. How many times would you expect it landed on tails? You expect it to be 50-50. Did anybody get 50-50? Good. That makes it easier. So, did anybody get 49-51? 49-51? So is that close enough to being 50-50? What do you say? Yeah? Okay. Did anybody get 48-52? 48-52? Is that close enough to being 50-50? Yeah? Did anybody get 47-53? 46-54? 45-55? Is that close enough to being 50-50? So that's the, I mean, you guys were very confident on the first couple. You're like, yeah, that's close enough for sure. But now we get to 45-55. You're like, yeah, maybe. Not sure if that's close enough to be able to just say 50-50. So that's what chi-squared analysis is kind of about. It says it's used to analyze data to see if what we observe, how many coin flips, what we observe, is close enough to being the expected value to say, yes, that's the expected. All right, so that's the short summation of it. So chi-square test, it answers the question, is there a statistically significant difference between the observed and the expected results? So the observed results are what you actually flipped your coin. The expected is what we expect to happen. Mathematically speaking, that's what we expect. We expect it to be 50-50. That's our probability. So the chi-square test, it's data analysis. It helps to answer that question, is there a statistically significant difference in the data? Or is that difference 49-50, is that just due to chance? I mean, it's not 50-50, but is that close enough? 48-52. Is that difference just due to chance? Or is there something else going on? Grab some highlighters. I think if we have 4 different colors, that might be helpful. I have highlighters somewhere. Do you have a little Ziploc bag in your drawer? I mean, I've got others. I can give you another Ziploc bag. This will get you for now. Just stick it in your drawer when you're done. Okay, formula sheet. Maybe I lied to you. 1, 2, 3 degrees of 4. I did lie to you. You do need 5 different colors. It was not intentional, but we do need something to box everything in. It just happened that way. So we've already boxed in mean, standard error, standard deviation, correct? We've got that in a color. Okay, so now we want to do the chi-squared stuff in a different color than what you have on the front here. So get a different color and box in chi-squared is this formula right here. Then we need just the table. So not laws of probability stuff. We'll look at that later. But this is what we're boxing in and use a different color. So, if an AP Biology test, if the test question tells you to set up a standard error graph or to set up a graph, whatever, then you have to draw a conclusion for it. Your R should absolutely include information about that graph. That's why they're making you do the graph. So if you do a standard error graph, your R should definitely refer to that graph and talk about those standard error bars. Do they overlap, don't overlap? The bars that represent the means, what do you see in that? You should talk about the graph. And then if the standard error bars do or don't overlap, then what does that mean? You should talk about the graph. So if you are asked to do a chi-squared analysis of data and you have to draw a conclusion, your R should include information about that mathematical analysis. And for chi-squared analysis, there are 4 things that you should mention within that. You should say what the chi-squared value is. Chi-squared value equals blah, 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 at such and such degrees of freedom, with a critical value of blank, and the p-value, the probability value, such and such. So you should mention those things within there. So I'm going to go through and show you where all of these things are at, and they're going to be highlighted in your notebook and on your formula sheet so you can flip back and forth and put those things together. Okay, so the first thing is the degrees of freedom. So I abbreviate stuff. I abbreviate so that it doesn't take me as long to write stuff down, because in AP Biology, time is not my friend, and on the test, it will not be your friend either. So this is not degrees Fahrenheit in this situation. For me, it's degrees of freedom. If this does not work for you, then don't do it. Whatever abbreviation works for you. So I've got to explain what degrees of freedom mean. Let's say we have a math problem. In my math problem, and don't write anything down yet, you can write it down in just a minute, just listen to my melodious voice for just a second. In my math problem, I have this number plus this number plus this number equals 15. That's my math problem. So, what could the first number be? Give me a number. Pardon? Yes. Sure could. Could it be a different number besides 12? Sure could. Okay, but we're going to keep 12 because I like 12. Second number. Now, come on. Hold on just a minute. Let me finish my sentence. Come on now. It's Friday. Give me something a little bit wackadoodle for this next number. Okay. Negative 0.35. Excellent. So could the second number be that? Yes. Could it be something other than that? Could be, but I like negative 0.35. Can this third number be anything? This number can be anything. This number can be anything. What does this number have to be? So, what does this number have to be? No, this one is negative 0.35. So 12. Yes, and I agree, but I don't like the 0.75. Oh, wait. No. Oh, okay, I'm sorry. I mean, and that's what I was doing in my head, that's why I wrote it down. But then what does this have to be? Say that again? Oh, yes. I'm sorry. 3.35? I'm sorry. I was doing the subtraction in my head, my bad. So 12 plus a negative 0.35 plus 3.35, but it has to end up being this last number. Make sense? This can be anything. This can be anything. This has to be 3.35. All right, so I have 2 degrees of freedom because this I have the freedom to be any number. This I have the freedom to be any number, but this must be a specific number in order for it to equal 15. You need to understand what degrees of freedom are. I can't tell you what notes to take. I'm explaining to you how we get degrees of freedom and what that means. All right, so highlight with a different color than what you boxed in. It doesn't matter if it's a different color from the rest of the stuff, just a different color than what you boxed in your chi-squared information. Highlight your degrees of freedom term. And then on your sheet, this is the information that applies to degrees of freedom. So it says degrees of freedom right here, but it's this row right here that represents degrees of freedom. That row and only that row. So the number of degrees of freedom we have is how many possible outcomes, how many possible choices we have minus 1. So I've got 3 possible choices for numbers. I take one away because this one had to be the 3.35 in order for them all to add together to be 15. So if you ever forget, it is on your formula sheet. Degrees of freedom are the number of distinct possible outcomes minus 1. For your coin flip chi-squared analysis, how many degrees of freedom will you have? So I've got a 2, I've got a 1. One of those answers is correct. Which one's correct? Why is 1 correct? Why not 2? Because I got heads and tails. Okay, so it's 2 possible outcomes. I can have an outcome of heads and an outcome of tails, but I only have 1 degree of freedom because it's the number of possible outcomes minus 1. Dice roll. How many degrees of freedom? Why are there 5 degrees of freedom? I have 6 possible outcomes that I could roll. So the number of possible outcomes minus 1. You looking at me squirrely? Does that not make sense? So if I roll the dice, it can land on a 1, it can land on a 2, it can land on a 3, it can land on a 4, it can land on a 5, it can land on a 6. That's it. I have 6 outcomes. When I run analysis of my dice roll data and it says how many degrees of freedom do I have, since I have 6 possible outcomes, degrees of freedom is however many possible outcomes you have minus 1. So my degrees of freedom for the dice roll lab is 5. if I have a bag of marbles and there are 10 different marbles in the bag, I have 10 different outcomes I could have. So how many degrees of freedom would it be? The number of possible outcomes minus 1. So it would be degrees of freedom would be 9 for the bag of marbles situation. All right, how are we so far? Okay. Next. Oh, let me do this. Chi-squared value. So you need a different color than what you highlighted degrees of freedom, different color what you boxed in your chi-squared information at. Your chi-squared value is essentially your answer to the formula after you do the math. Your chi-squared value is essentially your answer after you do the math. So on the formula sheet, this is my chi-squared value. And you can write it x with a little 2 exponent. So when you're doing your analysis, you can write x squared equals blah. That's your chi-squared value. So here's the formula that we're going to use. What does the big weird looking E stand for? How do you know that? It's right on here. So if you forget, it's right here. The big weird E in any of these formulas, that means the sum of all. What does the little O represent? Observed results. What does the E represent? Expected results. So we expected how many heads? We expected how many tails? Those are your expected results. Nobody got that, so you observed something different. 49, 51, 48, 52, whatever. And then so it's observed minus expected squared over expected. Here's where the biggest mistakes come in. People don't do sum of all, and people forget the squared part. That's where the biggest math mistakes come in. Okay, so that's our chi-squared value. Our chi-squared value is essentially the answer to when you do this math. All right, next, the critical value. The critical value is a numerical value, and it is telling you, you use that value to decide whether your null hypothesis was rejected by the data or whether the data failed to reject the hypothesis. So I don't like to write things out if I have a good abbreviation for it. So FTR, I know that means failed to reject. If that doesn't work for you, then don't use it. Or put FTR, and if this is the first time using it, in parentheses, put write out failed to reject, and that way you can go back and say, well, what does FTR mean? Critical value, how sure you are that you can reject or fail to reject the null hypothesis. So on the data table, and be careful with what color you use. You might just want to underline it because you don't want it to be so dark that you can't see the numbers. But all of the numbers that I have highlighted in blue, these two rows right here, those numbers represent critical values. So the first row are the degrees of freedom. The second two rows are the critical values. All right, probability. I can't imagine a time where we will use a probability other than 0.05. However, it is entirely possible that an AP Biology test question will say, analyze it using a probability of 0.01. The probability of 0.05, that means that I'm 95% sure that I can reject or fail to reject. There's always going to be some weirdo piece of data that's going to throw me outside of that 95%, but 95% is relatively well assured. And so for probability, that's p-value on the data table. And so this is all information about p-value, but I expect to always use the 0.05 p-value. I know on my problems it's always 0.05. However, it's entirely possible that you can see a 0.01. That's not out of the question. All right, so a really quick kind of summary of how to use this table, to apply the table, and then we'll start working on the math on this. All right, so let's say I run through this equation, boop, 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 and I end up, after I do the math, my chi-squared value is 0.75. I expect to always use the p-value of 0.05. If it's the coin flip, how many degrees of freedom do I have? If it's the coin flip, I have 1 degree of freedom. I expect to always use the 0.05. So where those intersect, that is the critical value for my particular experiment, for my particular data analysis. So in this situation, the critical value is 3.84. My 0.75 chi-squared value falls below the critical value. If it falls below the critical value, then I know that that my null hypothesis was the data failed to reject my null hypothesis. If it was 7.75, that's above my critical value, and I know that that means the data rejected my null hypothesis. And I think that's, okay, yeah, right here. So CV I know means critical value. My arrow up means my chi-squared value, that would probably be a good idea. Chi-squared is above critical value. Chi-squared is below critical value. If my chi-squared value is above the critical value, the data rejects the null hypothesis. If my chi-squared value is below the critical value, the data fails to reject the null hypothesis. So because chi-squared test, because this type of analysis answers the question, is there a statistically significant difference? The chi-squared test we're going to look at is going to evaluate a null hypothesis. That's what we're going to use it for. So null hypothesis means there's no statistically significant difference in the data. So whenever we say that the chi-squared value rejects the null hypothesis means there's no statistically significant difference in the data. If we reject that thought, then that means the difference in the data is significant. The data fails to reject the hypothesis. Null hypothesis says there's no statistically significant difference between the data. If we fail to reject that, then we're saying there's no statistically significant difference in the data. So we didn't get any 50-50. We had 49-50. Let's go all the way to 45-55. So we have 45-55. Just eyeballing it, like, maybe that's significant? We don't know. We run the math, we run through this, and we find out, after using our data table, let's say that we run the math and the chi-squared value ends up being above the critical value. That tells us that the 45-55, there is something going on to create those results. It's not close enough to be in 50-50 just to be 50-50. If we run the math and our chi-squared value is less than the critical value, that's saying that 45-55, that's just random. It's still close enough to being 50-50. The differences in the numbers are not statistically significant. How are we doing so far? Any questions so far? Yes. How many degrees of freedom do we have in the coin flip? That's the only number you look at. How many degrees of freedom on the dice roll? That's the only number you look at. So what we're saying is 3.84. If it's over that, it doesn't matter. Nothing else matters because 3.84 is the critical value. So that's the turning point right there. You don't look at any of the other ones for that situation. Good question. Any other questions? Okay, so add this last little bit of information. So when a chi-squared analysis rejects the null hypothesis, that means that, listen to my melodious voice for just a second. That means that change in data, 45-55, that means that there is some other outside factor maybe having an influence on it. Some variable that maybe you didn't control that you didn't realize that you needed to control. So if there is a statistical significance in that data, something is biasing that data or is influencing that data. All right, now you can write down. When the chi-squared analysis rejects the null hypothesis, that means the differences in the data are not due to chance alone. There is likely another variable having an effect. All right, so you may or may not have room on the spot where you collected data, and that's fine. But real quick, go through and get your totals. So how many heads did you have? How many tails did you have? Dice rolls. If you haven't finished the dice rolls, don't total that out yet. As soon as we get done with the heads, tails example, I'll let you go and you can finish that up. Then on the next clean page, just at the top, like do little coin flips so you know what data you have, do your heads, tails, and then write your totals in. Whatever your totals are. So, chi-squared formula is the sum of all of the O minus E squared divided by E's that we end up with. You need to do the O minus E squared divided by E for every outcome that you get. So I have two outcomes on the coin flip, so I'm going to do this twice and then add the values together, add the answers together. On the dice roll, you have 6 possible outcomes. You're going to do this 6 times, once for each dice roll, and then you're going to add that all together. So for my heads, and for this one, yes, we are baby steps, but this is going to give you a good resource to come back to look at. So I'm going to write heads, then I'm going to write O minus E squared divided by E. I observed 40 heads. That's probably not what you're going to write down. So you write down your observed value. Minus, how many do we expect? I expect 50 squared divided by 50. Write it out. (40 minus 50 gives me 10 squared over 50. Write it out. Do your math. Put it in parentheses, squared baby steps on this one so that you have a good resource to come back to. 10 squared is 100 divided by 50. My chi-squared value for heads, I'm not even going to do that, is 2. You're going to get something different. Use a calculator. Go to 2 decimal places, so number, point, number, number. Round to 2 decimal places. Do the same for tails. Write it out. Tails, O minus E squared, E. Write it out, baby steps, make it very visible for yourself to see so you have a good resource. I observed 60 tails. I expect 50 over 50. Oh, and this was a negative 10. Sorry about that. I kind of dropped the negatives on this because when you square it, what happens to the negative? Yeah, it goes away. So I kind of ignore them, but it's probably a better idea not to do that. I'm sure Mrs. Haas would probably say that at least. So I get 100 over 50. That gives me 2. Then underneath, write chi-squared equals the sum of heads plus tails. So my chi-squared value is 4. And your numbers are different. So you plug in your numbers. So now you've got this all nice and spelled out. So you see a 2, so number, point, number, number, 2 decimal places to the 100th place. So you have it all spelled out, a nice example. And so now you can see that in order to get your chi-squared value, you need the sum of every outcome that you work that math through. So 2 plus 2 gives me 4. So just looking at my data for just a second, my chi-squared value was a 4. How many degrees of freedom do we have? Okay, and what's our p-value? Okay, so where these come together, that's my critical value. So my chi-squared value is 4. The critical value is 3.84. Does that mean the data rejects the hypothesis or the data fails to reject the null hypothesis? Mine is 4. That's above 3.84. So that's saying that the data rejects the null hypothesis. So 40-60 is not close enough to 50-50. 40-60, there's something else going on, some other variable that's happening. Maybe I was just like dropping the coin. Well, I mean, I'm just saying that a lot of times that won't give you a really random answer because if you hold it the same way and drop it the same way, like if you control that variable, it'll probably always land on the same side. So that might be something that didn't give you a really random outcome. Whereas flipping it, it's at least turning a few times before it hits the ground, and it might bounce as well too. So that might end up being a variable. I'm not saying that it was or wasn't, but it could be. That would be something, and that's why I said, make sure that you do it a little bit more than just dropping it, because it might not. I might have absolutely no reason to have said that, but we want to make sure that we control every variable that might have an effect on it. Do you see how I got that answer? So if I were writing a CER for this, get to my reasoning would include the fact that my chi-squared value was 4, and that would be things that you would list for E as well. My chi-squared value was 4, so add a p-value, or probability, of 0.05 with 1 degree of freedom, the critical value is 3.84. Because my chi-squared value is greater than the critical value, the data rejects the hypothesis, and there must have been some other outside variable influencing the experiment. All right, so now run through yours. Use the data table. Tell me what was who had the 4951? Okay, 4951. Did you run your math through? Okay, so whenever you get your math run through, I want to know what was your flips, and I want to know what you say about, how would you evaluate. Go ahead, Jaden.